Okay, we're going to be looking at how to solve the two-dimensional heat equation in non-dimensional coordinates that we partially solved during class today. And so this was the summation of an infinite number of constants of integration Fn. And we had a xi dependence, which was a sine term, and our zeta dependence was a hyperbolic sine term. All right, we had one boundary condition left to use, and that was that the non-dimensional temperature at position xi and a specific position zeta equal to 1 was equal to 1. And so if we plug that into our governing differential equation, we have that the term containing xi has absolutely no effect. It's only the term containing zeta that we have to plug our value of 1 into. And so that just becomes sinh of n pi. All right, so at this point we have to solve for an infinite number of constants of integration, and we've just got this one boundary condition that we can use. So the trick we're going to use is called orthogonality, and it basically allows us to turn an infinite number of constants of integration into one constant. So let's draw a line under this. Here's the definition of the Fourier sine series. It is the integral from 0 to 1 of the sine of m pi xi. And the important thing here is the index. And the second term is n pi xi. And these indices are important only because they're different. And the summation, or the integral here, is equal to the Kronecker delta. And that's basically a function that says if n is equal to m, then this integral that I'm showing here has a value of 1. And if it's not equal to m, the integral is 0. So that's the definition of the Fourier sine series. It's kind of an unusual sort of thing, but trust me, this is true. We'll prove it later in the tutorial. And we can use this definition to simplify our governing equation. So we basically want to make our governing equation look something like the Fourier sine series so that we can, simplify those terms. So the first thing I'm going to do is multiply both sides of our equation by the sine of m pi xi. And here the index is quite important because I want the index to be different for the right-hand side of the equation. For the left-hand side of the equation, the sine of m pi xi times 1 is just sine of m pi xi, and the summation is the same. It takes some consideration whether I'm going to put the sine m pi xi term inside or outside of the summation, and it doesn't really matter because with respect to the sum over the index n, the term I'm multiplying by has an index m, and so it's basically a constant. So I can either, multiply my constant by the infinite number of terms and then add them together, or I can add them together and then multiply. To make it convenient for myself, I'm actually going to put this term I'm multiplying by, the sine of m pi xi, inside the summation. And we'll see why in a minute, but it doesn't really have much of an impact on the final solution. So now, what I want to do is integrate both sides of this equation from 0 to 1, and I don't really need to multiply by 2 because that factor would just fall out. So what I'll do is form that integration. Okay, and now the left-hand side is pretty straightforward. I can easily solve that. I know what the integral of sine is. It is negative cosine, even if I sometimes have to look it up. And then I have to divide by the constant multiplying c, which is m pi. And I evaluate that expression on the interval between 0 and 1. And so I'll go ahead and keep on working on this left-hand side. If I plug in those boundary conditions, so the first one is c equal to 1, so that's just the argument m pi. And the second one is the cosine of 0. All of this is over m pi. I can see quite straightforward that the cosine of 0 is 1. And I'll just rewrite this to make it a little tidier looking. So the negative of a negative 1 is a positive 1, and I've still got my negative cosine m pi, and all of this is over m pi. And this is absolutely correct. I can leave this form as it is, but if I want to be clever and sneaky, I notice that as m progresses from 1 to 2 to 3 to 4, the sign of the cosine of m pi keeps changing. So when m equals 1, the cosine is negative, and when m equals 2, the cosine is positive. And so I can actually achieve a function that does the same thing by writing this as negative 1 raised to the power m. And so maybe it's a simplification, maybe it's not. It's just a trick people do to write their mathematics differently. And to be clear, both of those solutions are absolutely correct. So you can use either of those expressions, whichever one you prefer. Now, that's the left-hand side. Coming back to the right-hand side of the equation, we need to tackle this Fourier sine solution. And so to do that, I think I'm going to write this, I'm going to start writing the terms in the summation rather than writing it as a summation. So we're looking at the integral of the first term for which n equals 1. And so we have f1 sine of 1 times pi times c times the sine of m times pi times c, because we've decided n is 1, but we don't know what m is. And our hyperbolic sine term remains the same. And now we add the second term, and that's f2 sine of 2 pi c. The sine of m pi c doesn't change, it's the same thing because, well, we don't know what m pi c is, and m is not dependent upon n. We'll squeeze in that hyperbolic sine, sinh, and so on and so forth. We keep writing this out for the infinite number of terms, and at the end we integrate the summation with respect to c. But what I want to do is to make this really look like the Fourier sine series so that I can invoke that property of orthogonality and get some traction with getting rid of this infinite number of terms. So I'm going to rewrite the first term in this integral. And I'm noting here that the constant of integration, f1, and the hyperbolic sine term both have absolutely nothing to do with xi. So here we are, just the first term. f1, hyperbolic sine of hyperbolic sine of n pi, but n is 1. And now the integral, the terms that have xi in them have to stay inside the integral, and that's pi xi and the sine of m pi c. And so that's just the first term in the series. And we could write an integral like this for every other term, for f2, for f3, for f4, for f5. But what we notice is that it looks a lot like the definition of the Fourier sine series. And in this case, unless m is equal to 1, this integral is going to be 0. Because remember, from the Fourier sine series, when n equals to m, the integral has a value. But when n does not equal to m, the integral has a 0 value. And so the one term we have that is non-zero in this entire infinite sum of integrals is the integral where m equals n. And so writing that, this is the one term that has a value. And just to be clear here, we've chosen n equal to m, so I'm going to change out that n for m to be meticulous. So now we've entirely written our solution in terms of m. And we can solve this equation pretty simply. You can write this as the sine squared of m pi c. But I'm just going to use the fact that if we come up to our Fourier series, we see that what our solution is basically some other constants times the integral of a sine squared and m. So the thing we're missing is that factor of 2. So this term is actually just equal to 1 over 2. And that, again, it's 1 because m equals to n. Our constant comes down, and so we'll multiply the integral value 1/2 by our constant. And yeah, we've pretty much tackled the right-hand side of equation. So to pull it all together, we were trying to solve for that constant of integration fm. And so now we have an equation. We set the left-hand side equal to the right-hand side. And we can actually just go ahead and write out the solution to this equation. And so bringing down the left-hand side first, we'll set that equal to this term that contains the constant of integration. And then we just rearrange the equation to solve for fm. So if we come back to the course notes, we can see that the solution to this constant of integration is an analytical expression that's defined for m values from 1 to infinity. And we can then use these to start to examine our solution. We notice that if you actually calculate these values, you only see a real value for odd values of m. So when m equals 1, 3, 5, 7, 9, so on and so forth, you get a value. Otherwise, that -1 term is for an even value of m, it's positive, and the numerator of the constant of integration is 0. So that's why all of the even terms in this series are 0. So I'm only going to consider the odd terms, because otherwise I'm just wasting my time with the calculation. So now if we plug in this solution for Fn back into the solution for our differential equation, we get the full final expression for our differential equation solution, for the solution to the differential equation. So we can write out like the first couple of terms for this solution. So for n equal to 1, I get that expression, for n equal 3, for n equal to 5. And so these are, I mean, they're long-winded expressions, but it's easy to actually start calculating this summation. And the first thing we'll look at is really how that constant of integration depends upon the index value. And you see that it falls off very rapidly. It goes from something on the order of hundredths to something 10 to the negative 48 over the course of 30 index values. So what we expect is that for each subsequent term in our solution, it's going to have less of an effect on the overall summation, because as you get to these smaller and smaller numbers and you're adding them together to big numbers, they're not going to have much of an effect. So now we'll start looking at partial solutions to the equation, by which I mean these indexed solutions like theta for n equals to 1 or theta for n equals to 3. And we're going to be considering a fixed value of zeta equal to 0.5 because to map this two-dimensionally, we have to hold something constant. So looking at these partial solutions, theta n, they're different from theta, which is the full solution. Theta n is an indexed solution. And the difference is, like these index solutions are, yes, they are solutions to the differential equation, but like we said in class, you kind of have to add them all up together to get to your full solution. So like, for example, if we were looking at the fifth index solution, it would be equal to that expression. And that is a solution to the differential equation. But what we really want is the summation of all the theta solutions, theta 1, theta 3, theta 5, because that gives us the physically meaningful solution. So if we come and look at these indexed solutions, we see that n equals 1 has the largest contribution, and n equals 3 and n equals 5 are quite small comparatively. And that is exactly what we expected, because we know that the constants of integration decrease very rapidly as the index number increases. And so these additional solutions are not contributing very significantly to the overall solution. And here we're looking at that overall solution, which is the summation. So I'm showing n equals 1, and then the next plot is n equals 1 plus n equals 3. And the next plot is n equals 1 plus n equals 3 plus n equals 5. That's what I mean by the full solution, when you're actually adding things together. And because it's symmetric, I'm not going to worry about the values for xi greater than 0.5. So now, looking at the solution to the full heat equation, we'll look at the first indexed solution, theta 1. I'll put that up here. And just a reminder that the top surface was what we called T2, and all of the other sides were at T1. And so we can see what we expect, sort of a radiating sort of shape to the pattern. What we have to be really careful about, though, is that whenever we have index solutions, if we don't add enough terms in the solution, we will not get the correct answer. And so there's these regions where the temperature gradient is quite large. Like any of these corners, you have T2 right next to T1, and so the gradient is quite large. And when that is the case, you need to calculate more terms in your solution. Otherwise, it will not converge onto a reasonable answer. And we see that if we look at the second solution, if you will, which is theta 1 plus theta 3. So we've added two terms in the series, and you get this sort of artificial dip, or like eyes staring at you, and that's obviously not physically true. That dip is an artifact of the fact that we haven't added enough terms in our solution to get an accurate equation in that region. Looking at the next term, if we add terms 1, 3, and 5, we still see that artifact, and that's telling us we don't have enough terms. It's not really until I added about 170 terms in this last one that I got an answer that converges on something I believe to be reliable. And even then, if you look at the corners, you see that there's this region where the temperature gradient is very, very sharp, and so the reliability of the solution in that region is not very high. Now, if we look in other regions where the temperature gradient isn't very high, we can expect to need fewer terms in our solution. So down here, where the temperature is not changing very rapidly, you can probably get a decent solution with 1, 3, 5 terms, and it will be reliable and robust. But up there in that region where the temperature is varying rapidly, you're going to need, tens to hundreds of terms to get a solution that is reliable. How do you know your solution is reliable? You have to choose a limit, sort of a precision limit, and I would kind of say maybe think about 1%. So if you can add another term to your solution and it changes by less than 1%, you're probably close enough to what I would call a reliable answer. But again, that will depend on the situation.